Hey guys, welcome back. Sorry to have missed so much time this week. My understanding is from looking at some of the attendance sheets that at least some of you or your friends have been in the same predicament I've been in. I certainly hope you're able to get a little extra sleep this weekend and get healthy. A few people asked me to go over some of the problems from the review sheet. The ones that kept coming up, I put them together in this format. Hopefully it helps. The first thing is on problem 4. We're talking about work is equal to the change in kinetic energy and the change in potential energy. So the total change in energy of a system is equal to work. So we're going to use that and go forward. We could also look at it as the initial kinetic plus the initial potential minus the work, the energy lost from the system, equals the final kinetic plus the final potential. Either way are good ways of looking at this problem. So if I do this, the work is lost from the system due to friction, is force times displacement, and change in kinetic energy plus change in gravitational potential plus the change in the spring energy. Keep in mind that there is no change in kinetic energy. The initial and final velocities are 0. There's no gravitational potential or initial spring potential because we've chosen our reference level appropriately. So force is mu Fn times d. That is, the work is negative Fd, so F is mu times force normal, which is mu times mg, and d is cosine theta d, mg cosine theta d. When we put the whole thing together in an equation where gravitational potential is negative mg d sine theta, and spring potential is 1/2 k d squared, because that's how far the object's moving. It's nice, excuse me, that d cancels out. So we can solve for the coefficient of friction is gravitational potential minus 1/2 kd over mg cosine theta. When we plug and chug, we will find that we get to 0.11, and I think on the answer sheet it's listed as 0.115. So I rounded a little bit, but that's how we do this problem. When moving on to the next one, I looked at 7, and here's the thing: we have an applied force and a friction force, and this is a great problem because we have a sum of the forces in the y direction, which is kind of cool. So we can find force normal equals mg, which is important because it's a friction problem. And then sum of the forces in the x direction, which is important as well. So we'll find Fa minus force friction equals ma in the x direction. The important thing to consider is there won't be any acceleration until Fa is greater than force friction. So until Fa equals force friction, it doesn't move. So we can set 2.4 t squared equals mu s mg, because it's not moving, it's static friction. And we solve for the time, and that's how long it takes for the object before the object starts moving. And it takes 2.47 seconds. And then we can look and say, hey, after 2.47 seconds, what happens? Now, you might be tempted to solve the fx equation for the acceleration, and then use a kinematics equation to find how far it will go. The problem is you can't use a kinematics equation because the acceleration is equal to the acceleration is not linear. It's non-constant, so the kinematic equations won't work. What needs to happen then is we need to take an integral of the acceleration between 2.47 seconds and 5 seconds to find out how far or what the velocity of this thing is. And what we're going to find is, wait for it, it's 12.6 meters per second, which is kind of cool. The thing that's great about this is we have a necessary free body diagram, which is big. We want to know the free body diagram. Then we do some of the forces equations. That's nice to know too. Then we have the object not moving for static friction, and then moving with kinetic friction, and then we have to integrate acceleration to find velocity, and then finally get the answer down here. I mean, how cool is that? I think it's cool. It's got a lot of different things to it, which makes it an interesting problem. Then finally we're going to get to problem 12. This one, as several people said they had trouble with it, I'm not sure it's a conceptual difficulty or a way that the question is worded. I think it might be a little bit of both. One is the question is looking for the velocity, or sorry, the acceleration of the object at 4 seconds. And I'm not drawing this drawing here to be particular to the initial velocity necessarily at the top, and it's gone 90 degrees exactly in 4 seconds. Just trying to show, hey, we start off with some velocity. Some amount of time later turns out to be 27.5 degrees. It's moving at 10 meters per second, and the radius is 50 meters. So then we go through, and here's the thing, this is the question's looking for. We want to find tangential acceleration, and that is in the tangential direction. We've gone from 2 meters per second to 10 meters per second in 4 seconds. So our acceleration is 2 meters per second squared. And then we also have a radial acceleration right here. And the radial acceleration is going to be equal to v squared over r. And at 10 seconds, basically v squared will be 100 divided by r, which is 50 meters. So we're going to get the tangential acceleration and the radial acceleration are both 2 meters per second squared. So the acceleration is going to be, by Pythagorean theorem, 2.82 meters per second squared. And I certainly hope that helps. I've had other questions about the handout I gave while I wasn't there, in fact, and I'll try to tackle that next. I definitely hope you guys are finding this stuff coming together as you go along in the weekend. And once again, for your health and your learning, try to get some sleep. All right, I certainly hope this helps. That's the best I can give you right now. I'll try to give you some more in a little bit.